theory of EM radiations. We know these are the radiations, these are energetic radiations which are coming out of any source of light or which are being emitted out by any charged particles. What is more important to note is that Planck was the one who actually combined all these facts about the EM radiations into the form of a theory, and that's called Planck's quantum theory of electromagnetic or EM radiations. Now, his observations can be listed in the form of points. His first observation was, or his first point is, that the electromagnetic radiations has both electric and magnetic field components which are always perpendicular to each other and moves in the direction of propagation. This can be explained with the help of a diagram, like if suppose this is the principal axis we have and this is the one of the components, let it be electric component, then the magnetic component is almost as like this. They are perpendicular to each other and both of these are moving in the direction of the propagation of the EM radiation. So this is the first thing to understand, that EM radiations has both electric and magnetic field components. The second point about the EM radiations is that unlike sound waves or water waves, EM radiations doesn't need any medium, and even they can move in the vacuum. So they doesn't need any kind of a medium. The next most important thing about the EM radiations is so that we can understand. See, the basic purpose of going into the postulates or the points of the Planck's quantum theory of EM radiations is so that we can understand this normal light, which we technically called EM radiations, in a much better way. The third point, the most important point, is regarding the EM radiations spectra. The electromagnetic radiations has a wide spectra. That is, it is of many types. Now, with the help of a diagram, I can show it to you. This is the EM spectra we have. Usually we see that we believe that electromagnetic radiations are only just the light. It's not the light. Light is only the part of a very big electromagnetic spectra, and the part which we see is basically a visible light which our eyes can detect. The spectra starts from actually long radio waves which are lying below the frequency of 10 to the power 6. Then we have radio waves which are actually starting from coming up to the end of the 10 to the power 8 frequency. Then we have what? Microwaves, infrared rays, visible region, ultraviolet radiations, X-rays, gamma rays, and in the end we have mainly the cosmic rays. The spectra is given in terms of the frequency, whose unit is hertz. The microwaves are till approximately 10 to the power 11. Then we have IR, which is actually lying between 10 to the power 12 to 10 to the power 14. Visible is at the range of 10 to the power 15. This is the very small part, and this is the only small part of the EM radiation spectra which our eyes can detect. And this visible spectra is divided into, we know, 7 colors, which are together called Vibgyor: violet, indigo, blue, green, yellow, orange, red. And in terms of wavelength, the range is from 400 nanometers to 750 nanometer. Then we have from 10 to the power 15 to 10 to the power 17 a band of ultraviolet radiations, which are highly energetic radiations. Then we have X-rays, which are again much more energetic radiations than the UV rays. And then we have gamma rays, which are the most energetic radiations we have, whose range are actually above 10 to the power 19, and they can go up to the 10 to the power 24. Beyond that, we have cosmic rays. So this is the complete electromagnetic radiation spectra, and only this small region part, which is called visible part, we are able to see. Even if we have radiations of some other frequencies or some other wavelengths which are lying in either before this visible or after this, we won't be able to see because our eyes cannot detect this. Now, after understanding the electromagnetic radiation spectra, let us now understand first the basic properties of the electromagnetic radiations, on the basis of which we distinguish one radiation from the other. The two basic properties on which we distinguish one radiation from the other are frequency, which is given as symbol nu, and wavelength lambda. Now let us understand these two terms. If this is the EM wave we have, the distance between two successive crusts or troughs is called the wavelength. Distance between two successive crusts or troughs is called wavelength, which is usually expressed in terms of meters. And since it's very small, usually we express it in the terms of either Armstrong's unit or nanometer. And if we stand here and if we find out that how many crusts or troughs are passing through this point in 1 second, it's called frequency. So it's the number of crusts or troughs passing through a point of a radiation in 1 second is called the frequency of the radiation. So basically, frequency talks about the speed with which the radiation is moving, and therefore its unit is hertz, which is also called cycles per second, because distance between one trough to the other trough completes almost a one cycle. So how many cycles are passing through a point in 1 second? So these are the two basic terms or basic properties on the basis of which we distinguish one EM radiation from the other. Now, according to this theory of EM radiations, the next point which comes out is that always for all EM radiations, the product of wavelength and their frequency is always constant and is equal to the speed of light. So the product of frequency and wavelength for any radiation is equal to the c, where the c is speed of light, which we all know is 3 into 10 to the power 8 meters per second. So the product of these two is always constant. Now this small formula clearly shows that frequency and wavelength are inversely proportional to each other. That is why in the spectra, when the frequency was increasing, the wavelength is decreasing. That is why in the visible region we have the wavelength from 750 nanometer to 400 nanometers in case of your this VIBGYOR. So these two terms are inversely proportional to each other. If we have a larger wavelength of any wave, of any radiation, the frequency will be small. If the frequency is small, the wavelength is large. They are inversely proportional to each other. The next point about the EM radiations talks about how they are emitted out and what about their energy. Next point says that EM radiations are never given out continuously. They are always given out discretely in the form of small packets of energy which are called photons or quanta. I'm repeating again, the EM radiations are given out or emitted out discretely in the form of small packets of energy called quanta or photon. Now this quanta is a word which was given by Einstein, and when we are talking about the EM radiations particularly, we say it's a photon. So they are never given out continuously as we usually observe. They are given out discretely in the form of small packets which are called quanta or photon. Now the next point is that the energy of these radiations or quanta is directly proportional to the frequency of EM radiation. It means what? This E is proportional to nu, which is the frequency of the EM radiation. Now as this energy is proportional to the frequency of the radiation, Planck said this proportionality is opened by a constant called h, or it's also called Planck's constant, whose value is 6.626 into 10 to the power 34 joule second. So this is how we can find out the energy associated with any of the EM radiations, which are given out in the form of small packets of energy which are called quanta or photons, and this energy is proportional to the frequency, and which becomes equal to E is equal to h nu. Also, we know that the wavelength and frequency are inversely proportional to each other. Like we know, frequency will be equal to c by lambda. Therefore, we can write this formula as E is equal to hc over lambda. So this suggests that the energy always is directly proportional to frequency, and it is inversely proportional to the wavelength. So the wavelength of any radiation, if it's very large, it will be having very low energy. If wavelength is very small, it will be having very high energy. and if the frequency is large, the energy is high, frequency is low, the energy is also low. So this is how we can do the usual interpretation, and now you can make out that since in the spectra the radio waves were having very small frequency, their energy was very less, and as we move from right to left towards X-rays, UV rays and X-rays and cosmic rays, the frequency got increased and it became up to the range of 10 to the power 24. Since frequency was very high, those radiations are having very high energy. That is why they are called highly energetic radiations. Even out of the 7 colors which we have, like Vibgyor, violet, indigo, blue, green, yellow, orange, red, we know this is 750 nanometers wavelength, this is 400 nanometers wavelength. So the wavelength is highest for red. So if wavelength is highest, its energy is lowest. So what we find is energy increases from right to left in the electromagnetic radiation spectra, wavelength decreases from right to left in the electromagnetic spectra, and the frequency increases from right to left in the electromagnetic spectra. So most energetic colored light is your violet light, because it's having the lowest wavelength and the highest frequency. So this is how we can make the interpretations out of this. Now after understanding this and after making this clear, the next point in the EM radiation talks about something which is very different. The next point about the theory of electromagnetic radiations is that it says that the quantas or the photons which are given out from the source are always given out in the integral multiples. It means what? That this E will be n times of h nu, where n is any positive integer. Remember, they are always given out. These quantas of photons are emitted out in integral multiples, like 1, 2, 3, 10, 15, 100, 200, 5,000, 10,000, like these numbers. It cannot be 1.5. It cannot be 2.5. It's like this. Always given out discretely in the form of integral multiples, which are n. So we can write this formula as E is equal to n h c over lambda also. With the help of this, we can find out that what is this n is. N gives us the number of photons or quanta released from any source. How many quantas are emitted out of light? How many photons of the EM radiations are given out or emitted out by a light? So that can be given out, that can be found from this n, because this n tells us the number of photons or the quanta emitted out. So these are the basic postulates or the points of the EM radiations, which was together were collected by Planck. But the next point, which was actually is the major, was given by mainly the Einstein, but collaborated or incorporated by the Planck, gave us a completely different picture about the EM radiations. The point talks about the dual behavior of EM radiations. Now this point, the new point, which is the last point of the EM radiations, is very different. It gave a completely new aspect to the EM radiations and their behavior. It talks about the dual nature of the EM radiations, which was first observed by Einstein. He was the first one who gave this concept, and this whole concept was incorporated into the theory by Planck. The point says the EM, electromagnetic radiations, shows dual behavior. That is, they show both wave-like as well as particle-like nature, which is well supported by the experimental proofs. Dual behavior. We always have thought that the radiations have the wave-like mode of propagation, they have wave-like properties. How can we believe that they have also a particle-like nature, which is a very, very different thing to be imagined. But it was the Einstein who, by his famous photoelectric effect, concluded that it is basically the EM radiations which are also having the particle-like motion or particle-like nature. Let us go into the details of these. Now, what all the supports and the proofs which we have for the wave-like motion, for the wave-like nature of EM radiations, we have the properties like reflection, refraction, interference, diffraction, etc. These are those basic properties which are only explained by considering EM radiations to be having wave-like motion or wave-like nature. So all these are the proofs of the wave-like nature of the EM radiations, as we can only explain these properties on the basis of their EM radiation or wave-like nature. But there are certain properties of the EM radiations which can only be explained by considering their particle-like nature. By assuming their EM nature or wave-like nature, we cannot explain those properties. The particle nature of the EM radiations are supported by certain basic phenomena or properties, like we have hot body radiations, black body radiations, and photoelectric effect. Or we can say the same thing in the other words, like the properties of the EM radiations like photoelectric effect, hot body and black body radiations can only be explained by considering its particle nature. It cannot be explained by considering its wave nature. So the particle nature of EM radiations is supported by the properties like photoelectric effect, hot body and black body radiations. See, hot body and black body radiations is a concept which at this level cannot be explained and cannot be made clear to you, to the class 11 normal students. It needs a very high level of studies, but definitely it can be explained to a little extent so that you can understand what exactly the hot body and black body radiations are. But of course, we can understand the photoelectric effect, which also has been explained in detail in our NCRT. So we'll take both of these one by one.